Good day, friends. Today we will be talking about patterns in Pascal's triangle. So let us start with Pascal's triangle. It's arrangement of integers. Pascal's triangle starts with 1. All the rows have 1 at the starting point, starting value, and 1 at the ending value. And for any interior number, if you have a look, say for 10, 10 is sum of 6 plus 4. The above two values sum up to the value. 35 is 15 plus 20. So this is the simple construction of Pascal triangle. It was first invented by Blaise Pascal, though we get the reference of Pascal's triangle in early literature also, but it's in the name of Blaise Pascal. So Pascal's triangle have a variety of patterns. So let us start with the patterns. What is Pascal's triangle? A triangular array of binomial coefficients. So these are the binomial coefficients nck. Nth row kth position has the value nck, which is a binomial coefficient. Each entry is a sum of the above it. I talked about it. For row n position A, the value is nck. The sum of the numbers in row is n is 2 to the power n. So if you look at the fourth row, 1, 2, 3, 4, fifth row, 1 plus 4 plus 6 plus 1 plus 6 plus 4 plus 1 is 2 to the power 4, because this is nothing but the expansion of 1 plus 1 whole to the power 4. These are the binomial coefficients, and the values of a and b are 1 and 1. So this is a plus b whole to the power n if you sum the nth row. Summation k equal to 1 to n, nck is 1 plus 1 whole to the power n, which is 2 to the power n. Now rows are palindromic. If you go from the left kth position or if you come from the right kth position, the values are the same because of the property that nck equal to ncn minus k. The number of groups you form by taking k objects from n of them is same as number of groups you formed by n minus k objects taking from n objects. Because whenever you are forming a group of k objects, the remaining ones are forming a group of n minus k objects. Choosing k element is the same as excluding n minus k element. So nck equal to n minus k, and the rows are palindromic. Diagonals and sequences. If you look at the diagonals, the first ones is all 1. Then the second diagonal is 1, 2, 3, 4, 5, 6, 7, the counting numbers. The third diagonal is 1, 3, 4, 10, 15, 21, n into n plus 1 by 2, which are triangular numbers. The fourth one will be the tetrahedral numbers, etc. So these are the properties of the diagonals of Pascal's triangle. I talked about binomial expansion a plus b whole to the power n, which is nck a to the power k, b a to the power n minus k to the power k. Row n gives the coefficients of a plus b whole to the power n, which is for the third row 1, 3, 3, 1. So if you look at the third row, it is 1, 3, 3, 1. Hockey stick identity. If you start from the diagonal, go down by by the other diagonal and stop anywhere, then sum of these numbers on the stick is the number on the blade, because of the identity r into r plus 1 cr plus dot ncr equal to n plus 1 cr plus 1. This is easy to visualize. If you form a group of r plus 1 taking from n plus 1 persons, whenever, and you put the tallest man at the end, tallest man of the r plus 1 groups at the end, then the tallest man should be there in the rth position or r plus 1th position, or nth position, and if you counting the number excluding the tallest man, you get the left hand expression, and on the right you get the number of groups taking r plus 1 objects from n plus 1 objects. And this is the hockey stick identity, and you can start from anywhere on the diagonal, go down a bit and then stop here. Then the sum of these numbers is the number on the blade. Fibonacci numbers are there in the Pascal's triangle. If you look at the diagonals, they call it shallow diagonals. Adding shallow diagonals gives Fibonacci sequence. So 1, 1, 1 plus 1, 2, 2 plus 1, 3, 1 plus 3 plus 1, 5. So that gives the Fibonacci number 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, etc. If p is prime, all interior numbers in the row p plus 1 are divisible by p. That's an interesting property. If you go to the 8th row, all the numbers are divisible by 7. 7, 21, 35, 35, 21, 7. All the interior numbers are divisible by 7. If you go to the 6th row, 1, 2, 3, 4, 5, 6. All the interior numbers are divisible by 5. If you go to the 4th row, all the numbers are divisible by 3. If you go to the 3rd row, all the numbers are divisible by 4. All the interior numbers are divisible by 2. So if p is prime, all the interior numbers in row p plus 1 are divisible by p. Sierpinski's triangle, if you color the odd numbers in the Pascal's triangle black and the even numbers as white, you will get mod 2 Sierpinski's triangle, which is the fractal looks like this. And you can go to mod 3, mod 5, mod 7, etc. Some other patterns: powers of 11. The nth row represents the digit 11 power n. Lattice paths NCK counts the paths in a grid. Probability row n shows distribution of heads in n coin tosses. Catalan numbers appear in the central binomial coefficients. I am not going to explain about that. I have run short of time. In the reference, let me say that this entire document is created by a single command in ChatGPT. Create latex slides on patterns in Pascal's triangle. I gave in ChatGPT, and it gave me all the code, from which I modified a bit, put the figures, and got this content. I'll stop here. Thank you. Like, comment, share, and subscribe my video. I am available for one-to-one sessions too. Thank you.